All right, welcome to the Explainer. Today, we're taking on a genuinely high-stakes engineering mission. We're tackling one of the most critical yet honestly frequently misunderstood challenges in renewable energy design, and that's safely matching a string of solar panels to an inverter. Look, you do this right, and you've got decades of clean, efficient power. Do it wrong? Well, you risk catastrophic hardware failure, blown inputs, or even worse. So we're going to break down the exact diagnostic workflow that real professionals use to nail this perfectly every single time.
Okay, let's dive into this. Here's our workflow for today. First, we'll define the solar sizing mission. Then we'll lay out our hardware specs, introduce our biggest threat, the winter voltage spike, calculate the absolute limit, look at how real-world safety margins work, and finally, we'll wrap up with a fatal flaw that beginners almost always make.
So, let's get right into part 1, the solar sizing mission, finding the perfect match.
Now, you might be wondering, what is the million-dollar question here? It's this. Exactly how many solar panels can we safely connect in a single series string to our inverter? It sounds like a super simple counting exercise, right? But it's actually this incredibly delicate balancing act. Put too few panels on the string, and your inverter just doesn't wake up in the morning. Put too many, and you will literally fry the internal components of your very expensive inverter the second the sun comes up.
The thing is, we basically have to satisfy two masters at the same time. We need optimal efficiency during those hot summer months to maximize our yield, sure, but way more importantly, we need absolute survival during extreme winter cold. It's a dual-threat narrative. We absolutely cannot sacrifice system safety just to squeeze out a tiny bit more power in July.
Moving on to Section 2, Hardware Specs and Data. Let's look at the raw numbers.
Now, what's really interesting about this baseline data is the story it tells before we even touch a calculator. We've got standard 450-watt panels here with an open circuit voltage, or VOC, of 49.5 volts. The working voltage, VMPP, is 41 volts. And notice that temperature coefficient, negative 0.28% per degree Celsius. On the inverter side, we have a single MPPT tracker operating between 200 and 850 volts. But look at that absolute max DC limit. 1,000 volts. That is a hard ceiling. We cannot, for even a fraction of a second, cross that 1,000-volt threshold.
Which brings us nicely to Section 3, the winter voltage spike. Time to introduce the villain of our story.
You see, solar panels are incredibly sensitive to temperature. When they get hot, they actually lose power. But when they get freezing cold, they push a lot more voltage. Now, standard factory test conditions always assume this perfectly pleasant 25 degrees Celsius, but out in the real world, we have to design for the absolute local minimum temperature our site will ever see. For our case study today, we're assuming a bitter negative 15 degrees Celsius.
Let's actually walk through the math here to see just how much this cold weather messes with us. Step 1 is finding our temperature delta. We take our absolute lowest expected temp, negative 15, and subtract that standard 25-degree testing baseline. That gives us a massive 40-degree variance. Step 2, we apply the panel's temperature coefficient. We take that 40-degree variance, multiply it by our 0.28% coefficient, and the result? A massive 11.2% increase in voltage on that freezing morning.
So, the absolutely crucial point here is that we cannot use that standard 49.5-volt rating to design our safety limits. We have to apply this 11.2% winter multiplier. When we do that, the maximum voltage each panel will push jumps up to approximately 55 volts. That right there is our real-world survival metric.
All right, Section 4, calculating the absolute limit. Let's see how far we can push our hardware.
18. That is our magic number, the absolute theoretical maximum number of panels we can string together. Let's look at exactly how we got there.
The formula is beautifully simple once you actually have the right winter data. You just take your inverter's maximum 1,000-volt limit and divide it by our newly calculated winter open circuit voltage of 55 volts. 1,000 divided by 55 gives us 18.18. And since obviously you can't install 0.18 of a solar panel, we have to round down. So a hard cap of 18 panels without instantly overvolting the hardware on a freezing morning. But hey, finding the max limit is only half the job, right? We still have to validate that the string will actually perform during normal operation. This is where we check the MPPT range using the working voltage, the VMPP, which is 41 volts. So, 18 panels times 41 volts equals 738 volts. Looking back at our inverter specs, the ideal tracking range is between 200 and 850 volts. Our 738 lands perfectly and safely inside that green zone, so the math is solid. 18 panels is completely technically viable.
Which brings us to Section 5, Real-World Safety Margins, Theory versus Reality. Because knowing the mathematical limit and actually building to it are two entirely different things.
The calculator literally just told us 18 is the maximum, but if you talk to any seasoned professional, they'll almost always dial that back and choose to install 14 to 16 panels instead. Why is that? Well, professionals rarely redline their hardware. Think about it like this. Just because your car's speedometer goes up to 160 miles per hour doesn't mean you should drive it that fast every day. Unless, you really enjoy buying new engines. We're building systems for longevity here, not just trying to pass a math test.
Let's look at how this logic actually translates into a robust design. The real world is just full of unpredictable variables. What if we get an extreme cold anomaly and it drops to -18? What about manufacturing tolerances where a panel actually outputs a little more juice than the sticker claims? Then you've got long-term system aging, minor deviations in the factory testing equipment, or frankly, just the need for an absolute safety factor. You absolutely need a buffer.
When we build out this safety margin, dropping from that absolute max of 18 down to, say, a comfortable 16 panels, we create these essential buffer blocks. We are making room for unexpected temperature dips, overperformance, and long-term degradation. It just ensures that no matter what crazy weather hits, the inverter's overvoltage protection will never trip. We're sacrificing a tiny bit of theoretical capability to gain absolute rock-solid stability. Finally, we reach Section 6, the beginner's fatal flaw. Let's talk about the single most dangerous mistake people make in solar sizing.
And this brilliantly illustrates what happens when someone doesn't understand the difference between survival and performance. A novice will very often look at their panel's working voltage, that 41 volts, and think, oh great, 1,000 volts divided by 41 is 24 panels. So they build a massive 24-panel string. Now, on a warm summer day, it might actually work. But on the very first freezing winter morning, that cold weather spikes the voltage, pushing a massive surge into the inverter, and bam! Total system failure. It's a literal fire hazard born from a seemingly simple math error. To make sure you never make that mistake, you have to rely on the twin pillars of system design. Pillar 1 is the winter Volk. That's your survival check. It verifies absolute maximums so your hardware isn't destroyed by the cold. Pillar 2 is the Vimpe. That's your performance check, keeping your operational voltage comfortably inside the inverter sweet spot for maximum efficiency. Both of these checks are absolutely mandatory. You cannot have one without the other. You have to survive the cold to perform in the sun.
So, as we wrap up this explainer, I want to leave you with one critical thought. Take a look at your own system designs, or maybe some plans you're sketching out for a future build. Did you actually calculate the winter multiplier? Did you leave a real engineering safety margin? Basically, are you absolutely certain your solar setup was built to survive the winter? It is definitely worth double-checking that math, because being mathematically prepared means the difference between a lifetime of free energy and a remarkably expensive repair bill. Keep learning, keep calculating, and I'll catch you in the next explainer.